Hey y'all, just wanted to give you a quick heads up before we jump in. There's some good news and some bad news from this archive dive. The good news is we had the lead author of the paper, Lillian Rang, actually join us for the archive dive this week, and we had a whole conversation with him. The bad news is we didn't get the audio. We chatted with him about a variety of topics, such as what were the most difficult things to build or scale, what's he working on next, hint, it's instruction fine-tuning, MOS, and the safety of the model. We also got his thoughts on how the Mamba layers interact with the sliding window attention. While it breaks my heart that you can't hear what he's saying, if you wait until the end, there will be footage of us talking at 8 times speed with some sexy romantic music in the background. If you want to join these dives live in the future and get to chat with some of the authors of the paper, please head to oxen.ai/community and join us live on these Fridays, or you can simply hop in our Discord and chat with us there. So sorry that we lost the audio on that. We'll do better next time. And with that said, let's dive in. Today's paper is hot off the presses, and it's called Samba from the team at Microsoft Research. It was released 10 days ago, so June 11th, 2024. And it is a great combination of transformers plus these linear recurrent models like Mamba, and kind of put all these building blocks together in order to be able to efficiently model unlimited context length, is their claim. This paper is called Simple Hybrid State Space Models for Efficient Unlimited Context Language Modeling. They open source all the code here on GitHub. And I love this little quote on the GitHub page. It says, Samba is a simple yet powerful hybrid model architecture with unlimited context length. Its architecture is frustratingly simple. So Samba is Mamba plus a MLP layer plus sliding window attention plus another MLP layer. And we've done dives into Mamba and sliding window attention in the Mistral models. So we won't go too deep into each one of those, but we'll give intuition about how stacking all of these things together makes for an efficient model that can also model unlimited context length. So why Samba in the first place? We all kind of know that infinite context length is one of the dreams of large language models, and transformers suffer from this quadratic computational complexity, making the infinite context length problem computationally infeasible. There's been other models such as linear recurrent neural networks that are great for speed, but lack the ability to remember details really far back in its context. And models such as Mamba are a breed of these linear recurrent neural networks that are based on state space models that claim to be able to model much longer sequence lengths. And so what Samba does is try to combine these Mamba layers with sliding window attention and multi-layer perceptrons to create a model that has the best of both worlds. And we'll kind of see what the authors claim each section of the model does as we go along. So at a high level, you can think of a Samba as these four building blocks that we're putting together. So Mamba, MLP, sliding window attention, MLP. And if you start to understand these as building blocks and the motivation behind each layer, we can see how this leads to a gain in performance in both accuracy and throughput. So they scale up Samba to a 3.8 billion parameter model trained on 3.2 trillion tokens, and show that it outperforms previous state-of-the-art purely attention-based models or pure state space models. So not only does it outperform it in terms of perplexity, all the way up to a context length of 1 million tokens, but it maintains a high tokens per second throughout that generation process. So you can see like Mamba models have a lower throughput than Samba models, and then like your regular Llama 3 will just run out of memory once you get to these bigger context lengths. So within each one of these building blocks, I really enjoyed how the paper kind of broke down what each layer was responsible for. So the hybrid model consists of three main layers: the Mamba state space, which they say is great for speed and modeling recurrent sequences. They add the sliding window attention on top of that, which they say helps for retrieval within that giant context. And then the multi-layer perceptrons sit on top of that, and they say that that stores a lot of the factual knowledge within the model. And as they do this, they actually set up a few different configurations. So they have Samba on the right here, where it's Mamba, MLP, sliding window attention, MLP. They do another version where they just take out this MLP layer in between the Mamba and the sliding window attention. And then they do Mamba plus MLP and just like pure Mamba as well. So we won't dive too deep into the math for Mamba since we did that in a previous dive. But at a high level, you can think of it just as like a recurrent neural network. And Mamba is like heavily inspired by gated recurrent units. And I like to kind of think of it in this sort of diagram where you have a hidden space that you're updating over time, and you might have a sentence like the quick brown fox jumps over. And as you're going along that sentence, you're having to selectively decide what you keep within that hidden space to be able to predict the next word. And so you can see we keep we keep quick, we keep brown, we keep fox, and then at some point we're going to have to decide what context we keep within the hidden state and what context we get rid of. So this is just like discrete with colors going in here. Really, these hidden states are continuous, and you won't have to completely forget one of the terms, but the point remains the same, is any of these recurrent neural networks are going to have to decide what to keep and what to get rid of. And Mamba layers claim to do this really well and really fast in a family of architectures called state space models, or SSMs. And the problem with this is the fact that this hidden state is going to have to allocate or decide what we're going to keep and what we're going to get rid of. So that's where they kind of add in the sliding window attention, and the sliding window attention helps them process longer sequences and let the Mamba layer kind of specialize in what it does best. So again, we also went over sliding window attention in our Mistral dive, but just to ramp you back up on that, in your regular vanilla attention, you'll have this n by n matrix where every token attends to every other token in the sequence. With sliding window attention, you set a window size within there, and say, in this case, it's like a window size of 3. And then as you're stacking the layers on top of each other, they can actually pass information within that window size through to the later layers. So some rough math, like from the diagram above to drive this home, is you might have the sentence, "The cat sat on the mat," and the first layer sees the cat sat, the second layer sees on the mat, and the third layer sees and watched the if you continued this. And so within that Mistral paper, they do some quick math, and they say, like, if you have a window size of W and you have K layers, then it's really just K times W is how much information can, in theory, gets passed through all the way to the top. So if you had yeah, we have a question.
Yeah. Basically, like I think like the issue with this, right, if I remember, is that like you have to deem the information important enough to encode, right? So
Yeah.
like the mat might not actually be like important in that window, but it might be important later on. I think that's the problem with all of these like linear attention mechanisms is that like you you can't know ahead of time what's important.
Yeah, totally. And so that's where they kind of say combining this recurrent layer with the sliding window attention kind of lets each of them specialize in what they can do
Hmm.
best. So they have like a nice sentence describing this in the paper where they say uh, Mamba captures the low rank information about the sequences through recurrent compression. So trying to compress some information in that hidden state. And then this leaves the attention layers in Samba to theoretically only focus on information retrieval from earlier in the context.
That makes a
So
lot of
they're,
sense.
yeah, so they're hoping to split them out there. And then finally, they have the multi-layer perceptrons within
Right.
here.
Sorry, before you move
Yeah.
on, Mike also has a hand up too.
Yeah, just going back to the sliding window, and Evan, the problem you mentioned that also relates to the attention sinks paper. Basically, that was their solution um, for it was uh, basically using that first up to four sync tokens, basically like a CLS token would work in an encoder model to capture all that information that falls out of the sliding window.
Totally. Yep. I think these are all, it's interesting when you read all of these papers, all of the ideas start to kind of converge around similar concepts.
Yeah, I was talking about like issues with tokenization, and I think ultimately like tokenization is somewhat related to compression. Like why you can't necessarily train a bit level uh transformer. And I think it's kind of the same thing. Like ultimately the transformer wants to operate on like as dense information as possible. And not giving it dense information seems to really affect the performance.
Interesting. Yeah, I feel like tokenization is always an underlooked part of the whole process.
Basically, there was a paper that was showing that came out recently that was showing basically like how G-zippable your data set is. Um,
Mm,
like if the compression ratio was higher, like your data was able to be compressed more, it wouldn't be as good for training. It's kind of like a massive, and I was trying
oh,
to relate that to tokenization, and if you think about it, um, it seems like tokenization and gzip are fairly similar things. They're both kind of building out like a Huffman tree based on like the frequency of parts in
mhm,
a word. So like tokenizers typically use like less information, or they use smaller encodings or smaller numbers for the more common tokens.
right.
Zeroth token will show up the most often, which is very similar to what gzip is kind of doing, where it's extracting the most common pattern and then using less bits to represent that with some lookup table.
Yeah. Do you have that paper somewhere? That'd be awesome to put in the chat.
Yeah, sure.
So
Cool.
I'm actually completely rebelling against what you just said with my byte level approach.
Okay.
Um, so in terms of compression, normally you think, okay, it's a byte, it's 8 bits, right?
Yeah.
Except anybody who's worked with UTF-8 knows that the like for English, nothing's going to be more than 7 bits per character. And when you get to multi-byte characters, if you go to like just using the ORD built in Python, that compression goes even further. So I'll maybe at some point get to a point where we can talk about that at a water cooler. But there is actually a lot of by combining bytes and bits and ordinals, you can actually achieve pretty good compression just at the byte level.
Nice. We should definitely add that to the agenda of the next
Definitely.
water cooler. Love to dive deep into that. Cool. Um, so with that all being said, they kind of try four different models sizes. So everywhere from 400 million to 3.8 billion. And they train baseline Mamba, Llama 3, and Mistral type models to compare it against. The first chart that they have in here is not apples to apples in terms of model size or training tokens, but they just wanted to show the performance on the classic suite of benchmarks against models that are even larger and have been pre-trained on more tokens. And they seem to outperform on a lot of the benchmarks there when they purely train on this Phi-3 dataset with 3.2 trillion tokens. And so thought it was interesting, this row, Samba's 3.8 and only trained on 3.2 trillion tokens and outperforms Llama 8 billion that was trained on 15 trillion tokens. And so then the next question is, what if you compare the same thing with consistent model sizes and consistent training data sizes? So in this case, they take the Phi-2 dataset, which is 230 billion tokens, and they train Llama 3, Mistral, Mamba, and Samba all around the same parameter count because you can't get it exactly the same with the different architectures. And Samba also outperforms most of these models. And you can see it's either some variation of maybe not the full Samba, but maybe Mamba sliding window attention MLP or Mamba plus MLP that all get the highest scores with the same configuration. So something about combining those layers together really does seem to help the model specialize. And then the next thing they explore is, Mamba isn't the only type of linear recurrence, like Evan was alluding to earlier. There's like a bunch of different models that claim to have this linear scaling factor. So they also compare it against Llama 2 with sliding window attention, sliding RetNet, and sliding GLA, which are models that I haven't actually read the papers for, but have this kind of linear recurrence. And they show that Samba, in terms of perplexity, outperforms all of those while maintaining training speed that's relatively competitive with all of the other approaches. It looks like the Llama 2 with sliding window attention is slightly faster to train because it's more parallelizable. Sliding window attention plus a transformer. With these models, you still have the linear layer within it, so it is a little slower, but it gets higher perplexity or lower perplexity. And then they also have some nice charts on the throughput compared to other models, and I thought this was interesting. So Mistral 1.6b actually has the highest consistent throughput throughout, and Mistral is like purely that sliding window attention. So adding this, linear layer in the middle does reduce the throughput a bit. And then like pure Mamba, which is the orange one here. So pure Mamba's orange, Samba's blue, and Mistral is purple here. So definitely crushes the pure transformers as the prompt length gets longer, but pure sliding window attention is faster than just the combination with Samba. But that being said, Samba outperforms Mistral on passkey retrieval. So even though Mistral might have higher throughput, it starts to fail on this passkey retrieval task as you get to longer sequence lengths. And that task is simply a pretty simple language modeling task where they will require a LLM to retrieve a 5-digit random number in a long meaningless sequence of text. And you can see that the recall for Samba is on the left here, and the recall for Mistral is on the right here, and it starts to stop finding that passkey as the context length gets longer if you just do the sliding window attention. So a lot of things that they're balancing here, like throughput versus retrieval of long sequences, but this does seem to be, so far, the best combination of techniques we've seen to optimize for throughput and optimize for long retrieval and stable language modeling all at the same time.
So it makes sense that that Samba would be slower than just sliding window because in the Mamba block, what is there? There's like a 2x and a 4x expansion in there, I believe, right?
Yep, I think you're right. So that was kind of the main takeaways I had from the paper. I will stop the recording here so we can kind of just freeform chat about it. And thanks for everybody that's watching on the YouTubes. Appreciate you.